Well, now that we've looked at the operation of the engine, of how it actually works, we're going to delve in a little bit in this module on some of the theory behind the engine. And I know that word theory scares a lot of you, and we're not going to go to the point of being engine designers, but I really want you at the end of this to understand where that efficiency number comes from. And so we're going to spend quite a bit of time on this module looking at that efficiency, looking at the theory and where the limitations are. And again, I want you to be thinking like engineers and thinking about how we might be able to stretch this a little bit and what kind of innovations should we see to make better use of the fuels that we have. So that's your challenge as we think through this. So we're going to look at the thermodynamics and then look at the energy usage and efficiency. So we'll do some calculations and everything in this module. So first off, let's look at the thermodynamics. So if we spend some time on this graph, and you've seen these PV graphs before, pressure versus volume, and this is the PV graph for an engine cycle. Now I want to draw a couple extra lines on here, and I'm actually going to start with a point right about here, because there was a fellow named Otto, O-T-T-O, that came up with a cycle, a PV cycle, and said, you know what, we could make an engine work if we followed a cycle like this. And so this is the Otto cycle, where we get automobile. That's kind of the roots of all that, but there's one of the first cycles that that somebody came up with to look at how an internal combustion engine would work. And so his thought was, hey, if we can put some fuel in a cylinder and we start down here at bottom dead center, we're going to compress that cylinder. We'll compress the air-fuel mixture to some point. And again, this is the spark ignition engine, so we can't compress it too much or that fuel is going to auto-ignite like we talked about before. At this point, we reach our maximum compression right here. We're going to ignite the fuel. The pressure jumps way up in that piston, and now we're going to drive the piston back down. And so coming down the top side, this is our expansion stroke, or the power stroke, where we get the power out of it. And then we have a short little blip down at the end here, and that's going to be our where the valve opens up, and then you get that pop, and that's where the engine noise comes from. So our pressure doesn't go all the way back down to atmospheric pressure. We still have some pressure in the cylinder when that exhaust valve opens. So that's the Otto cycle for spark ignition engines. Well, fella named Diesel, and that was actually his name, where we get the name diesel fuel, he said, hey, if we could come up with a way to get those pressures higher in the cylinder, we could get more energy out of this thing and more power. And so he came up with the idea of that fuel injection. So we just compress the air, we can allow the pressures to get much higher in the cylinder and get up to this point. And so we get higher pressure, and his curve, what he envisioned, would go like this. So as we inject that fuel, the fuel is going to be burning as the cylinder comes down. So we kind of have a maximum pressure. We hold that pressure there until all the fuel is burnt, and then we continue that expansion down there. And so this was the diesel cycle, when, again, another person envisioning how we might be able to do an engine. Well, we know what really happens is a combination of those two, really in all of our engines. So we don't get a real clean jump up here like the Otto cycle, the diesel cycle. We don't keep a constant pressure as that cylinder expands. We know that when we light that fuel, we're going to get some pressure. And so really what happens is this combination cycle, like it's actually drawn on there on the on the original drawing in the background. Again, compression stroke coming up from the bottom, and we actually see the dimensions on the top up here. So we see this clearance volume that we talked about. So that's as the lowest volume that we can get up there. If we get much lower than that, this curve, of course, is turning asymptotic, and so our pressures would go really, really high, and we would start to reach physical limits of the engine. When we start to break stuff, it's going to start to explode. So that's kind of the pressure where we get to. We ignite the fuel. They're going to get an immediate pressure increase. When that fuel ignites, as the piston starts moving down, we're going to get some expansion then at a more constant pressure. And then the power stroke after the burning is done, and that pressure is just pushing the the stroke back down. All right, now nothing in real life works square and with square corners like that, so really what's probably going to happen is that we're going to see something more rounded in there, and this is going to depend on the fuel type in there, the energy that's going on, but probably what we're going to see is more of a rounded type of a performance like that. So what you see on the red line, and the pressures might jump, and it'll vary a lot. So that's more in reality what we would see in an engine there. So that's kind of that's the PV cycle. That's a drawing of what actually happened there. So now let's think about this a little bit. And if I was to have a shape on there, and we do have a shape, and I wanted to look at the area on a PV diagram. So think about what the units with that would be. So if I calculated area is going to be, on this curve, is a pressure times a volume. All right, so what are the units? Pressure times a volume. Units of pressure are a force per unit area. So that would be, the area is a length squared. So it would be force per length squared. Volume then is what? Volume is a length cubed. So we have an L cubed over 1. So if we look at those units, what they end up to be is a force times a length. Think about what is force times length. That's energy or work, or energy actually. And so we could have units here in English. It would be like foot-pounds. In the metric system, it would be a Newton meter, which is a joule as well. So that would be equivalent to a joule. So that is the amount of energy. So if we got area on there, we can look at amount of energy. So if we look at the PV diagram, go back over there, the area in between these two curves, or inside that loop, either the square loop or the red loop like I've drawn there, that area is the amount of energy that is produced by that engine. And we actually have a term for that we use. It's called the indicated mean effective pressure, P sub I M E, indicated mean effective pressure. And that can be calculated from the PV diagram as the area under the diagram, area under the PV diagram, so I'll say area sub PV, so that's the area between those two curves, divided by the volume of the cylinder, so V sub C, so the displacement, if you will, of that cylinder there. And that gives us the pressure, like an indicated mean effective pressure. And now we can take that pressure and go straight to power. So the pressure, that's the pressure that's on the top of the cylinder. So if you look on the right there, on top of that piston, that's the pressure that's acting on the top of that piston. So if we look at that pressure, we can convert that to a force. We can calculate what the force is. So we can look at the force down on that piston is equal to the pressure, that mean indicated effective pressure, times the area of the cylinder. And that's just pi r squared of what that area would be of that cylinder. That gives me the force that's pushing down on that cylinder. Take that one step further. How much work am I doing? The work that is being done by that cylinder as it's moving, so the work is a force over a distance. So I take that force that I just calculated right above there over the distance. What is the distance? That's the stroke of the cylinder. That's how far it moves. And that is the work. So that's going to have units of a Newton meter or something like that. So that's energy, Newton meter. If I want to get that into power to see how much power I get out of it, so capital P for power, the power then can be calculated by the work that I just calculated above there, but I got to put a time on it. So the work is how many of these strokes that I get in a unit of time. So I can do that times the angular speed of that engine. And now we have to hold off just a little bit and be careful about what we do with that angular speed, because remember, on a 4-stroke engine, I get 1 power stroke for every 2 revolutions of the crank. So I have the compression, the power, the exhaust, and the intake. And so that's 2 revolutions of that crankshaft. So the amount of power is actually divided by 2. Now, here's where you can see the big difference. If we put the 2 in there because we have a 4-stroke engine. If we had a two-stroke engine, we wouldn't need to divide that by 2, and that's where we can see numerically how much more power we can get out of a two-stroke engine. So that's how we could look at the PV diagram, and if we could do that, and engine designers and engineers that work on engines will be measuring these pressures and looking at them, looking at how much power they're getting out of, how to manipulate and shape these curves, because the way we get more power out of it is to get more area in between those curves, to stretch that out, make that bubble a little bit bigger there, okay? Now keep in mind a couple things. All of the area underneath that curve, so if we look at the area underneath that curve, this is basically lost energy. This is the energy that we have to put into that engine basically to compress the gas. So whether it's the air or the air-fuel mixture, it's also the energy that we would need to inject the fuel and so forth. So there's a lot of parasitic type loads that are in there. So that's all the area below there that we have to make the thing burn, to make it work. Okay. Now the other thing that we don't see, that we forget about, again, this is a 4-stroke engine. So down on the bottom here, there is a line, that horizontal line that goes back and forth, and we often ignore that. Remember, 4 strokes. We look at the curve up here, the lower curve on the PV loop. That is the compression stroke. Then we have the power stroke coming back down, but now we have to have the exhaust stroke. And so that's where we would come out across this line like that for the exhaust, and then we have the intake, and we would come back the other way for the intake, so we would actually suck it in. Now, we know there's going to be energy loss there because it's going to take some energy to force that exhaust out of there. So actually we're going to get a kind of a loop like this where we're going to see pressures up fairly high going out to push the exhaust out. Then we're going to see the pressure come down sort of negative below atmospheric because we're sucking that in. So we have to have a vacuum to be able to draw the gases in. So we're actually going to have a little loop down here. And guess what? The area inside that loop is also energy, but that's all lost energy. And so we can start to see how this all shapes together. So we have a number of different pieces that go into this PV diagram to understanding what goes on in the engine. And again, here's where people that are designing engines and working on this stuff, they're going to spend a whole lot of time trying to understand that PV diagram and understand how to manipulate it. What could I do differently in the engine to push that compression curve down and widen it out? How do I keep the pressures higher longer to get more energy out of it, to expand it? What can I do with that loop on the bottom that's all lost energy? How do I squash it, make it smaller? Okay, and one of the things, again, we talked about turbochargers in the last module. That would be a case where instead of drawing a vacuum when that piston's coming down, I'm actually helping to shove the gas into that piston as it's coming down. So that's going to give me a little bit more pressure in there. So that's going to manipulate and change that curve and make it look more like the exhaust curve, therefore less losses. So there's a lot of things we can do, and that's why we look at that PV diagram. That's why it's so important. That's why in your thermodynamics class you wonder, why are we messing around with these things? What does it matter? This is why it matters. Here's where we go as engineers to understand what it's working, what it's doing, and how to make it work better. Okay, so let's look at those efficiencies just a little bit more. Let's tear this apart now. We have this efficiency curve here, and this is a nice indication of where everything goes. So if you look at coming from the left, this P sub Fe number there, that is what we call the fuel equivalent power. So that is how much energy or how much power is in the fuel. Okay, so this is fuel equivalent power, and you see it defined down there. So if you're looking at the fuel coming into the engine, this is thermally what it contains. If I burn it in a calorimeter and checked, how much energy was in there, how much thermal energy I could recover, that's what would be there. Okay. Now we see as that energy comes in, I'm going to lose some of it. So if I go clear to the right, let me look at clear to the right. This P sub B number is what we call the brake power. And the term brake comes from the dynamometer, and we talked about the dynamometer a little bit. You work at that in lab. It's just a big old brake that puts a load on the engine, and so when we measure power, we use a brake like that to measure power output, and so that term is kind of stuck with that power. So this brake power, that's the useful power. power. That's what I can do something with, get out of the engine and work with, okay? So that is the brake power. So that's what we got. So we got all these losses down in here. So what is this big loss that comes down to the lower right here? This is rejected heat. This is the stuff in the PV diagram. That's the theory, going back to that, to saying, hey, you know, we have to compress the thing. This is the shape of the curve. This is all going to be lost power, and it's going to be as rejected heat. That's why the engines get hot. It goes out as rejected heat, goes out through the exhaust, goes out through the thermal, you know, the conduction through the walls of the engine and so forth. Okay, so this is rejected heat. So in between each one of these, we have some efficiency numbers. So this eta sub IT, that is the indicated thermal efficiency. So this is the thermal efficiency of the engine based on the PV cycle, based on the theory of the dimensions of the engine cylinder and so forth, the pressures that we're developing in there. So this is all the power that we can get out of it. So this P sub I then up here is the indicated power. So that's what would be available theoretically from that engine. But then we have a lot more losses and so forth in here that are going to be mechanical type losses. So in this curve, they call that the friction power. So those are friction losses. So, and a lot of it is friction. It's bearings that have to turn and so forth. But there's also some cooling that has to go on in the engine. So we have to pump water through an engine jacket to keep it cool on a lot of our engine designs. So that's all going to be a parasitic load. We often have a radiator in front of the engine with a fan, and we attribute that to losses. So all that are losses, and it comes down to what we can get out of this thing. Okay, so that is what the brake power is. That's what we can ultimately get. So the brake power, and let's put some equations down. You can see how they're related here graphically, but equation-wise, this is the way that they relate. So the brake power is equal to the indicated power, and let me reset off. So the indicated power times the mechanical efficiency. So I'm taking the brake power here, relating it to the indicated power, and what is being lost is the mechanical efficiency here. So that's how we work those together. Likewise, we can say that the brake power, let's see, so we're going to look at the indicated power. The indicated power, how it relates to the fuel equivalent power. So the indicated power is the fuel equivalent power, so what's coming into the thing, times that indicated thermal efficiency. So those two relate together. So how do I go all the way from the front to the back? Well, we have another efficiency that we define as the brake thermal efficiency. So it's kind of a combination of the two. Eta sub BT, that's the brake thermal efficiency, and that relates the brake power to the fuel equivalent power. And so it can be calculated as the multiplication of the mechanical power times the indicated thermal power. So it's all of those together. And this is the one that we're usually interested in, that we really want to look at. And so it is the brake thermal power, brake thermal efficiency is the brake power divided by the fuel equivalent power. And that's what we look at a lot for engine performance. So we look at what we have put into the engine, how much fuel we put into the engine, and how much energy is there, what the flow rate of that fuel is as it's going into the engine, and we look at how much we get out. And so that's an indicator of how good we've done as engineers setting up an engine, designing it, minimizing friction, and all those kind of things. So let's put some numbers on this to really understand what it is. So if we look at energy usage, and here's the fundamental equation that we work with. This is the way that we can calculate, look at how much power is actually in our fuel. So if we look at this, we have this equation. The fuel equivalent power is equal to this H sub G times the M dot F is the mass flow rate of fuel. H sub G is what we call the gross heating value of the fuel. Gross heating value. So that is, I take the fuel, I put it in a calorimeter, I burn it, and I see how much energy is there, what kind of energy I get out of it. Now there is a thing called the net heating value, so I'll mention that because we can kind of get confused. So H sub N is the net heating value of the fuel. The difference between those two is that when we burn a fuel in a calorimeter, there's going to be water as a byproduct, and the question is, do we recover that water as a vapor, or do we condense it, which is going to take energy to condense it back to a water to water form, and recover it as water? So that gives us a little different indication of what energy is available. So the gross heating value, this one we actually recover the water as a liquid. So we're going to account for the fact that there's going to have to be some energy there that changes the state of the water back to the liquid when we recover that water. Okay, so that's the difference there. So the fuel equivalent power is going to be in units of horsepower or kilowatts, depending on where we're working in the English or the metric system. The heating value of the fuel is going to be, in the metric system, is going to be like kilojoules per kilogram. So that's the units that you would see there. How many kilojoules of energy are in a kilogram of that fuel? And we can play with units, and we'll do an example here where we look at those different units to understand what's going on and how we calculate it. So we can do it on a mass basis, we can do it on a volume basis, and so forth. So that's the equation that tells me how much power is going into it. And then to get the efficiency, I need to measure the power that's coming out. So let's look at that tractor. I have that picture up there. That's one of the tractors that we have, one that we're going to be working with in lab quite a bit, putting on the dynamometer and abusing and so forth. But if I look at that tractor supposedly will give me a power output of about 72, if I look up, and we'll talk in class in another time on where we get these numbers, but it will give me a brake power output of 72.47 kilowatts. That's what it should produce. So that's its capabilities, all right? Now I can also look up and find out that to do that, it's gonna burn, so the fuel usage rate, and this is actually not m dot sub f, so this is actually gonna be a volume, so the fuel usage rate is gonna be 6.18 gallons. And I'm going to mix up units just on purpose here, so gallons per hour. So if it's going to produce 72.47 kilowatts of power, it's going to burn a little over 6 gallons in an hour of fuel. All right, so from that, can I figure out what the efficiency of that engine is? So I need to figure out what is in that fuel and how much I'm getting out of it. So if we look at that fuel, and we can look this up on the internet or where, and I'll show you where we can find the exact fuel specifications when this was tested. But typically the gross heating value for diesel fuel is about 45,500 kilojoules per kilogram. That's how much energy is in the fuel. So let's figure this out. Use our equations. Fuel equivalent power right here. So P sub Fe is going to be equal to the gross heating value of the fuel. So let's start with that. And I'm going to work out units here. So 45,500 kilojoules per kilogram times, and now I need the mass flow rate of fuel. I don't have the mass flow rate, so I'm going to have to work with a density somewhere. So let's just put it in here. Let's put what we got. We have 6.18 gallons per hour. All right. Now I got to do some conversions. Gallons and metric and English, we got them all mixed up. Let's go to the metric system. So how many liters in a gallon? So we have in my notes to make sure, 785 liters per gallon. All right, so that's going to cancel my gallons off, and I get rid of that. So I have now liters per hour there. I need to get that in a mass because I have kilograms. So what is the density of fuel? I can look up the density of the fuel, and it is 0.835 or 836. And that is kilograms per liter. All right, so that gets rid of the liters. And that also gets rid of my kilograms because they're up here. So what units do I have left? I have kilojoules per hour. And I need to think about what is it that I'm looking for. And I usually write that down first, and I didn't do that. But typically, I'm looking for power as a watt or a kilowatt. And a watt is a Newton meter per second. A Newton meter is a joule. So that's also a joule per second. So I can leave the joules up on top, but I need to get the seconds, the hours into seconds. So I need one more conversion here. So I need to go 60... or 1 hour, excuse me, this shouldn't be in the numerator. Let me erase that. So I need to go 1 hour for every 60, not 60 seconds, 3,600. 3,600 seconds in an hour. The hours cancel off. I'm left with kilojoules per second. And if I calculate that and get that number, that tells me that that is 247 kilowatts. Okay, so, and I left the kilojoules up here. I left the K in there so that I end up with kilowatts instead of watts. So that is how much power is in the fuel that's going into that tractor when it's producing. Wow, look at that, 247 kilowatts going in, I'm getting 72 out. So what is my brake thermal efficiency? If I take a look at that, ATIS of BT, ATIS of BT we said was the brake power divided by the fuel equivalent power, and that is 72.47 divided by 247, and that's about 29%. So we're essentially using about 29% of the energy that is available in that fuel to run that engine at that condition. Okay, 29%. So there's room for improvement, engineers. Let's see what we can do to solve that issue to make that a little bit better. Okay, so that's engine. Now a couple things about this, and I went through this example. I used some goofy units here with gallons and mix it up. And one of the things that your textbook does that I really don't like, and I want to make sure that we're clear on this, your textbook uses a lot of magical units constants, I call them. So they'll have an equation there and then they have a number plugged into it. And that number is for converting the units. And so you have to be careful when you use that equation to always plug in everything in the exact correct units. And I wish the textbook didn't do that because that gets us in trouble more than not. So if we're always careful and lay out these equations, so that equation that you see on the slide over there in your textbook has a units constant underneath it. I think it's 60,000 or something like that that it puts underneath it to convert the units from what they want in that equation. So you're going to see me throughout the class use equations without those units constants. We're going to work through the units. We're going to keep track of what's going on so that we don't get messed up in terms of what's going to be happening or how to build these equations and watch the units as we go through. So that's one lesson that I want to make sure that we remember and do carefully throughout the semester here. Okay, now let's take a little bit closer look at this. Again, this is for this particular tractor operating at 72.47 kilowatts. Now this tractor, that's its maximum capability. So that's what its rated power is, or the maximum amount of power that I can get out of it. What would happen if I'm not using all of the power out of that tractor? How much fuel would it use? And so I want to take a look at this fuel map, what we call a fuel map for an engine, or an efficiency map for a particular engine. So let's delve into this a little bit and spend a few minutes discussing this. So here's a fuel map for some kind of an engine, and it's a relatively small engine. You can see that the maximum output's about 40 kilowatts, so it's a lot smaller than that tractor that we just looked at there. So it would be a small utility tractor or something like that, maybe on an air compressor, portable air compressor, or something of that nature. But this shows us a number of different things. You recognize the outside curve here, at least the shape of this outside curve, and this is torque versus speed. So it's the torque curve that we looked at earlier that you're going to collect in lab and so forth, okay? And so we've got this shoulder up here where we reach governor's maximum. The peak power is probably going to be right in there somewhere, or the maximum power point. But this graph also shows us a couple other things. It actually shows us where the power is. And so you see these dotted lines that kind of scoop back through the curve. These are lines of constant power. So let's say, for instance, that with this particular engine, I was only needing about 20 kilowatts at this time that I was operating. So for whatever job I'm doing, I bought a bigger tractor than I need, a bigger engine than I need, or whatever. So it's not utilizing the whole capacity of the engine. It's only using about half of it, if you will. Now these dark lines that come this way, and I'll extend these out here, these give us the fuel usage. If you look at the units up in the center here, this is essentially that brake thermal efficiency, or it's another way of expressing it. It's how many grams of fuel that I use per kilowatt hour. So it's the amount of fuel that it takes to develop a certain amount of power. So 200, and the peak in here, I guess, would be about 275 grams per kilowatt hour. So we're operating down here at about 400 grams per kilowatt hour. So we're not operating very efficiently. The engine could operate much more efficiently up in this point. So what I might be able to do is to slow the engine down. So if I slow the engine down, I still am going to need to develop 20 kilowatts. So let's say that this was a tractor pulling something through the field, and it was a bigger tractor than I need, and I don't need much tractive effort to pull it. So what I might be able to do is use a higher gear on my transmission so that the wheels spin faster, but now I'm going to slow my engine down. And what that'll allow me to do is move back along here. So let's say that I slow my engine down to like this point. I'm still developing 20 kilowatts. I've still moved back on this curve to this point right here. But now look at my fuel usage. I went from about 400 grams per kilowatt hour to 300. So I've basically had a 25% decrease in the amount of fuel that I would be using to accomplish the same job. And this becomes a real critical issue, and something that we're going to be thinking about through the whole semester as we look at the efficiency of engines. Because a lot of times we will want to use it, and an engine will be set up, and obviously for a certain peak power and for a certain application. So for instance, a lot of our equipment runs on hydraulic power, and we'll look at fluid power, we'll look at hydraulics. Hydraulics will only operate efficiently if I run them at a certain speed. So basically on a machine that's hydrostatically driven, I'm going to get in that machine, I'm started up, and I'm going to turn that engine to its maximum speed. And that's where I'm going to operate it all day long, whether I need all the power out of it or not. Because if I slow that engine down, the hydraulics don't work very well. They become extremely inefficient, and so the whole system is going to be more inefficient. And that's one of the things as we move forward in the industry is really looking at the electric drives and other things, because electric drives afford us the opportunity to slow that engine down. If I don't need all of the power out of that engine, I can actually slow that engine down a little bit, run it a little bit slower, and be able to get more efficient use out of it. If I need more power, then I can speed the engine up. The electric drives and the electric control systems in between will be able to compensate for all that. And so there's a lot of opportunities and a lot of growth that we're seeing in the machinery industry that way to try to become more efficient overall, not just making the engine more efficient, but to make the whole system more efficient. So that's a quick look at the theory, looking at some efficiencies, and what we're going to do the next module is delve in a little bit more into the combustion process. How does this fuel burn, and see what's happening, and that's going to lead us to understanding some emissions and other things that's coming out of the back of the engine.